Let's see. Okay, everybody, if you could quiet down, that'd be awesome. You're probably going to want to write some of this down. Uh, as an intro, let me pose this question to you. Excuse me, guys. If we were going to make emergency power kits out of these little solar suitcases, and we were talking with a school administrator, and they said, hey, here's what I want. If there was a power outage, I want to be able to light every classroom, hallway, and bathroom, and we need power in the nurse's office, and we need a computer, all powered by batteries. Is it feasible to ask for that? We don't really know. We don't have a way of talking about this stuff yet. So today we're going to learn about how we talk about that. And then we'll figure out what we could power off one of our little kits. We're going to learn the vocabulary that's up here. We're going to learn about amps, which is electrical current. We're going to learn about volts, voltage. We're going to learn about watts, which is a measure of power. And we're going to learn about charge, which is amp hours. So first, current. Current is the number, not literally the number, but it measures the amount of electrons going through a wire or through a circuit. So it'd be kind of like if you had a tank and a pipe and a water wheel, it'd be like the gallons per minute going through the pipe. So it's how much, it's a measure of how much electricity is moving. You could kind of just say amps are like gallons per minute through a pipe. That would be one way to talk about that. The more amps, the more electricity there is. Have you guys ever heard the fact that static electricity is like, it's something like 10,000 volts? You know, when you touch a doorknob and it sparks you? And you think 10,000 volts, that's going to kill you. But, or if you're folding laundry fresh out of the dryer on a cold morning, sometimes it's all sparky. That's static electricity. It's super high voltage, but very, very low amps. If it was high amps, then you would die. But high voltage just makes it jump across the gap and spark you, but it doesn't kill you because amps, the high amps are what would kill you. Here's another way to think about amps. Here's the same waterfall 2 different times of the year. On one picture, we got a lot of water coming over. On the other picture, not very much water coming over. So which one has more amps? Which has more current? The A, right? That's the one that has a lot more water going over the side. Current can only be measured when a circuit is running. You can't measure the current on a battery. It'll cook your meter. Yeah, it doesn't. I don't want to do that. So our second way of measuring electricity is called volts or voltage. And volts is the pressure behind that electricity. So imagine if you have a pipe with water going through it, the water could be going through slowly, or it could be going through fast, like pushing hard on the water wheel, or like on the pipe analogy, have you ever taken a hose, put your thumb over the end? Even if the hose isn't on very strong, it could spray water pretty darn far. And that's increasing the voltage by putting your thumb over it, and then the pressure shoots it out. So here's a question. Which of these waterfalls would represent higher voltage? I heard a guess for B. Here's the thing. Voltage is pressure, not how much is going through. So A has higher voltage because that water is falling a lot farther. Another way to think about voltage would be if you drop a tennis ball from 6 feet in the air, it's going to hit the ground harder than if you dropped it from an inch off the ground. And so that's just another analogy. But the pressure, if you were under that taller waterfall, the water would be hitting your head harder than if you were under the short waterfall. So it's not how much power is going through, it's how much pressure it's being moved with. Voltage can be measured and should be measured when the load isn't attached. You just measure. You can measure the voltage on a battery. There's no problem. You measure between the positive and negative sides of a battery. And our systems are going to be 12 volts. So there's some components we have, like this light bulb we have, that this 12-volt light bulb, we just plug it in, no problem. If we were going to charge a cell phone, we'd need one of these little adapters that adapt 12 volts down to, it changes 12 volts down to 5 volts. You either use one of these in a car, or your car automatically has the 5-volt USB jack already. A lot of cars do. And then if you wanted to power like regular things, like something that plugs into the wall, normally you need something called an inverter, an AC inverter. It converts the alternating current from the wall to direct current, or vice versa. Okay, and then power is, I'm going to skip this slide. Power is the amps times the volts. So they were doing a little thing. I didn't make that slide. But right here's the formula. And I asked you to get your notebooks. The thought was you might write this down. Watts is power. Watts equals amps times volts. You need to know that formula. And so here's an example. Our solar suitcases come with a 0.4 amp light bulb, and they're running 12 volts. And if I said, hey, how many watts is that light bulb? We can figure it out. Just plug in what you know. I'm going to always give you 2 out of the 3 things. So, hey, if watts equals amps times volts, then in this case it's 0.4 times 12, which you just then use a calculator, and that's 4.8. Again, just 0.4 times 12. No big deal. Questions? I see a lot of you, like with your hands on the mice, you're doing things on the computers. You really should just be paying attention. It's just a little silly to, I'm going to ask you to know this stuff. Let's do another one. If you have a 60-watt bulb and you're using it at home, you're plugging it into the 120-volt wall outlet. How many amps does this bulb use? How do I set this up? Anybody? We got watts equals current times voltage. What formula do I write? Oh, you didn't have your hand up. I was so optimistic. Yeah. Thank you. Yeah, exactly. 60 equals amps times 120. Thanks, Jeffrey. And you guys, you've all taken enough math to solve this. This is a simple algebra problem. We're always going to have 3 variables, and you would get 2 of the 3 be handed to you. So how do you solve this? Divide both sides by 120, and then you have amps equals 60 divided by 120, or 0.5. So a 60-watt bulb, like you often have at home in a lamp or, light fixture running on 120 volts, is a half an amp of power. And then our final term for today is amp hours, or charge. And it's pretty simple. It's just the number of amps times the number of hours. And it's a lot like how much water is in the tank. But it's really, we're talking about how much charge is stored in a battery. So when you use power from a battery, the battery's charge goes down. The battery isn't magic. It just holds power through a chemical reaction. But 1 amp hour is equivalent to using 1 amp worth of power for 1 hour. So it's pretty, amp hour is just amp times hours. And if I said, hey, how many amp hours charge would you need to provide 1 amp for 3 hours? It's just 3. 1 times 3 is 3. So it's current times time equals the charge. Or amps times hours equals amp hours. That's all it is. But this is helpful when we're thinking about a system, like how long would it take to recharge this battery if I used it all night, ran it down, and now the sun's out? How long would it take to charge up? Well, we're going to talk about this. Let's say we have a 10 amp hour battery and it's all charged up, and at 11 in the morning we have a power failure, and then we're going to use that battery for the rest of the school day till 3:30. 0.4 amp light bulb, we're going to use it for 4.5 hours. How much charge will be left in the battery? We started with 10 amp hours, and then we can figure out how much we're using by doing 0.4 times 4.5. So current times time equals charge. We have the 0.4 amp light bulb going for 4 hours. That means we used 1.8 amp hours. And then if I'm saying we started with 10 and we used 1.8, then we're down to 8.2. I got one more example. Let's say we have our battery, we used power down till it's halfway empty, 5 amp hours left in the battery. And our solar panel produces 2.8 amps of current when it's in full sun. How long will it take to charge the battery up? We'd say 2.8 amps, that's what the panel can produce in full sun, times we don't know how many hours equals 5 amp hours. And then how do I solve this problem? Basic algebra, 2.8 times x equals 5. I'm literally going to wait till somebody tells me what to do. You divide both sides by 2.8. Thank you. Yeah, 5 divided by 2.8. So, again, the answer, I don't know why, 1.8. So it takes just under 2 hours to charge up half of this battery. That's how it works. So then a summary of what we just talked about today. Current, or amps, is the amount of moving electrons. This, 1 amp isn't 1 electron, but it's a measure of the electrons. Volts talks about the pressure pushing the electrons. Watts is a measure of power, and watts equals volts times amps. And amp hours is just the number of amps times the number of hours, but we call that charge also. Any questions? Thanks. Yeah, very good. So what we've got now is I've got a Google form. It's got 10 questions on it, and I'll post it in just a sec. And to get full credit, you just have to get perfect score. You can do it as many times as you want, or as you need to. This during the class period. After the period's over, that's whatever score you have is the score you'll get. And then when you finish the form, find your partner and go finish the toothpick bridges. About the last 20 minutes of class, we'll put them to the test. I look forward to seeing how your guys' bridges do. Let me say one thing about the bridges. One